Hello everyone, my name is Abhishek Vivekanandan. I'm working as a research scientist with SOTA Coaching Center in Informatics. The topic for today is plausibility verification for 3D object detectors using energy-based optimization. One of the motivations for this topic is that problems arising out of false positives in a real world. The probability of fluid-end collision increases if the object detector produces false positives and also frequent ghost detections, which leads to an uncomfortable riding experience for the passengers, making false positives on equal risk to the false negatives. To address these concerns, in this work, we have developed a parallel module which verifies the object's existence using mathematical priors. The model consumes three different types of information, including LiDAR point clouds, RGB information from the cameras, and ground level information extracted using RANSAC algorithm on LiDAR point clouds. We also use four different types of energy functions. I will give an explanation into each of these energy functions in the upcoming slides. But in total, we use four different energy functions. And then the methodology involves the three broad steps towards checking for an object's existence. Starts with obtaining the 3D bounding box coordinates from the base 3D object detector. With the coordinates, we can use the mathematical priors to verify object's presence by combining it with the energy minimization framework. The first prior is the Chamfer distance energy function. In Chamfer distance energy function, we measure the compatibility of the observed point clouds with the shapes constructed using the TSTF from the ShapeNet dataset. We use 5 components from the PCA to describe the shape of an object, and when an optimization is run, we find the best shape which minimizes the energy value. Here, the phi mean is the mean shape obtained by concatenating all the class car found in the ShapeNet dataset. The second prior is based on the sill-out intersection over union. In SDEF, or the sill-out based differential energy function, we measure the compatibility between two different segmentation masks, where one mask comes from the scene through mask RCNN, and the second mask comes from the projection function. The projection function captures the mask by applying ray casting on the optimized shape obtained from the previous step of the Chamfer distance energy function. And then the third and the fourth priors are based on the height and the rotation of the bounding box. The figure A shows the how the energy value is higher for directions which are farther away from the ground. Figure B shows the similar aspect when the bounding box is not aligned with the normal vector of the ground plane. Figure C and D shows the result when an optimization is applied. This is the overall architecture of our module. Each layer emits a certain energy value extracted out of an energy function. These independent energy functions are then combined with an alpha value, which represents the weight vector. The alpha value represents the impact of individual energy function towards the overall energy equation. The algorithm in the first step, we get the inputs from the base neural network. The second step involves pruning the directions by passing them through filters. These filters are based on the bounding box sizes and distance from the ego vehicle. And then the third step involves matching the segmentation mask with the bounding boxes. Fourth and the fifth step involves applying configuration value C1 and C2, and then extracting the energy value out of it. Right now we have uncalibrated energy value from which we need to find the threshold value to satisfy the objects. As a result, we constructed our own synthetic data set by applying augmentation on the new scenes data set to identify the threshold value. As you can see from the graph, for an EV or energy value of 0.5, we were able to find a balance and capture most of the false positive detections without compromising on the true positive samples. To showcase how well our model performs against the state of the art, which in this case is monorun, we have plotted the precision recall curve as you can see from the figure 4 and 5. With and without the impact of sensor fusion into the base neural network. As you can see, our model produces a higher area under the curve when compared with the base neural network, establishing the strength of our approach in reducing the false positives without compromising on the false negative aspects of the detections. So to conclude, we have 3 major contributions. The first one involves designing a modular parallel checking module. The second one involves developing a 2-step optimization scheme via the energy minimization framework, which in turn led to a significant reduction in the number of false positive samples via our decision-based rule filter. Thank you.